determinants, eigenvalues and eigenvectors. What else? What else you have learned? Cayley-Hamilton theorem. Yes? What else you have learned? Solving homogeneous and non-homogeneous system of equations, right? Okay. So I'll just give a brief of all the topics once, then we'll do the problems. Okay? We'll see even some MCQs related to that. Okay? Because we don't know exactly in what form the questions are going to be in your exam. Okay? So we'll try to do both. Okay? Both solving that completely or just MCQs. Both the ways we'll try to do, because this is the first time maths is being asked in the placement interviews. Okay, that written does. This is the first time, and we don't have any idea, okay, regarding that, because what is going to be the pattern we don't know. Okay, so we'll try to do that in both the ways, MCQs as well as in long and short answer types. Okay, so in matrices, yes, you have learned about different types of matrices, right? Okay, different types of matrices: rectangular matrix, square matrix, scalar matrix, diagonal matrix, identity matrix, and so on. Okay, so just I'll give a rough glance of all those things. I don't want to take much time on that. Okay. What is this type of matrix? Diagonal matrix, right? Then what is this type of matrix? Is that identity matrix? No, it's a scalar matrix, right? Diagonal matrix, if all the elements except the diagonal are zeros, all the elements except the diagonal are zeros, then it is called as a diagonal matrix, right? If all the diagonal elements are same, then it is called as a scalar matrix. Same, I did not say 1. Okay, if I write all the elements as 1, then identity matrix, right? Then we'll move on to the next, that is transpose of a matrix. Transpose, what is a transpose? Interchanging rows and columns of a matrix will become transpose of a matrix, right? Then you have learnt about symmetric matrix, skew symmetric matrix, symmetric and skew symmetric. If after interchanging rows and columns, you will get back the same original matrix, then we call it as symmetric. If after changing or if after interchanging rows and columns, if you are getting minus of the original matrix, then you call it as skew symmetric matrix. Okay, A transpose equal to A, then symmetric. A transpose is equal to minus A, then skew symmetric. Okay, then you have learnt about orthogonal matrix. Orthogonal matrix, A into A transpose is equal to A transpose into A is equal to I, then orthogonal matrix. A transpose equal to A, symmetric. A transpose equal to minus A, skew symmetric. A transpose into A is equal to I, or A into A transpose equal to I, then we call it as an orthogonal matrix. Similarly, for this is for the real matrices, right? So you will have these concepts for even complex matrices. There you are going to learn about Hermitian, skew Hermitian, and unitary matrices, right? Yes. For complex matrices, first you learn about conjugacy, conjugates, finding conjugates. Do you remember? A plus IB, its conjugate is A minus IB, right? So when you are dealing with the complex matrices, you have to find out conjugates, then you have to take the transpose, okay? Then that is denoted with A theta, like this, A conjugate transpose. If it is equal to A, then we call it as A conjugate transpose equal to A, we call it as, what do we call? Hermitian matrix. A conjugate transpose equal to minus A, skew Hermitian. A conjugate transpose into A into A conjugate transpose equal to I, then it is called as, yes, what it is called? A into A conjugate transpose equal to A conjugate transpose into A equal to I, it is called as, what it is called? See that you have learned here symmetric, skew symmetric and orthogonal for the real matrices. For complex matrices, the same concept is being carried over here, except that here we need additional, that is conjugacy. First we find out conjugate, then its transpose. If it is equal to A, then we call it as Hermitian. If A conjugate transpose is equal to minus A, then we call it as skew Hermitian. A conjugate transpose into A is equal to A into A conjugate transpose equal to I, then we call it as unitary. Then we call it as unitary. Okay? Then, do you remember the properties of transpose? Transpose. AB whole transpose. AB whole transpose. B transpose into A transpose. A plus B whole transpose. A plus B whole transpose. Yes. A plus B whole transpose. A transpose plus B transpose. Okay. Then we'll see singular, non-singular. Okay, before going to the actual topic, just I'm giving the brief of all the topics what you have covered. Okay, singular, non-singular. When we call a matrix as singular, singular, non-singular. If the determinant of the matrix is non-zero, then we call it as non-singular matrix. Okay. If the determinant of the matrix is non-zero, then we call it as non-singular matrix. Non-singular. Determinant of A not equal to 0. Singular, determinant of A is equal to 0. When the inverse of a matrix exists? When the determinant of A is not equal to 0. Okay? Whenever the matrix is non-singular, then it is invertible. Its inverse will exist. Do you remember A inverse is written as adjoint A by determinant A, provided determinant is not equal to 0. Determinant of A not equal to 0. Okay. Then we'll come to the actual topics now. Do you remember triangular matrices? Triangular matrices. Upper triangular, lower triangular, because we need that in LU decomposition. What is this? Upper triangular, right? Reverse way if I write, lower triangular. Okay, this is upper triangular, this is lower triangular. If it is in any one of the forms, we can call it as a triangular matrix. Okay. You all know how to find out determinant, right? Yes. Find out the determinant, because we need that in finding ranks. General method to find out rank. -1, 2, 3, -5, -6, 7, 8, 5, 10. And see even the time, how much time you are taking to do that. How much? 376. We'll see how many answers we'll get. 376. Yes, from the last I want the answer. What is the determinant? 376. Right? Yes, rank. Do you remember roughly how we calculate ranks? How many methods you have learned to find out rank? How many methods you have learned to find out rank? 3 methods. What are they? Echelon form. Yes. Echelon form, normal form, and the general method to find out the rank. Okay. PAQ form was also there. So concentrate on the echelon form because we are going to use it, okay, in solving the system of linear equations. Concentrate on that much. Normal form, okay, is a lengthy procedure. It may not be helpful for you, okay, for this exam. So better concentrate on the echelon form and the general method. Do you remember the general method? How we find rank? Yes? If the determinant of any matrix is non-zero and it is of order 3, then what will be its rank? 3. A is of order 3, okay, and it is non-singular matrix, then its rank will be 3. If suppose it's a singular matrix, then can you say it as 2? No. Can you say it as 2 when it is singular matrix? No, it should be, what do you call? Can I say that as rank as 2? No, it should be, what should I call that? I cannot say that as 2. If the order of the matrix is 3 and the matrix A is singular, then what will be its rank? Okay, you should write there less than or equal to 2. Okay, you should not say it as 2 because it can be still lesser than 2 also, right? So you should not write there 2. It is less than or equal to 2. Okay. Now, how we define rank? Do you remember? Rank. Yes. One sentence like this. Rank of a matrix is said to be R if there exists at least one highest non-vanishing minor of order R. Highest non-vanishing. Okay. Suppose you have a matrix of order 3. Matrix of order 3 and determinant of that matrix is 0. But determinant of matrix 2 by 2, submatrix 2 by 2 is non-zero. Okay, at least one submatrix of order 2 by 2 is non-zero, then I can say that the rank of the matrix is 2. I defined in the same way. Rank of a matrix is said to be R if there exists at least one highest non-vanishing. Okay, at least one highest non-vanishing minor of order R. Non-vanishing means determinant should not be 0. here instead of using the word determinant, he is using the word minor there, minor. Okay, there should exist at least one highest non-vanishing minor of order r, then we can say that its rank is r. Okay, so here we have learnt how to find out rank in three ways, that is general method, which is just based on direct determinants, based on determinants we can do. But see that determinant method fails when we have a rectangular matrix 3 by 4, 4 by 3 and all, right. So we cannot use determinant method there. Then second one is we have echelon method or echelon form. Third, normal, but it is lengthy, so we can avoid it. Just I will give the brief explanation of that once, okay, because it is lengthy, it may not be asked in your exams, or don't use it unless and until specified, okay, because echelon is easy to get the rank. Try to use it or try to use general method to find out the rank. Okay, if it is a square matrix, try to use general method. If it is other than square matrix, then try to use the echelon form. Okay, don't use the next one because it's lengthy. Okay, so general method, I'll give you one or two questions, then I'll move on to, okay, write the question based on general. I collected few questions. Find the value of k, find the value of k such that rank of the matrix 1, 2, 3, 2k7, 3, 6, 10 is 2. 1, 2, 3, 2k7, 3, 6, 10 is 2. You have to find the value of k. Okay. Now look at that question. It's given as rank is 2. It's a matrix of order 3. But see that its rank is less than 3. So when will it happen? When the determinant is 0. That is, the matrix is singular, right? So calculate the determinant, equate it to 0, then you are going to get the value of k. Okay? If the rank is equal to the order, then the matrix is non-singular. If the rank is less than its order, then the matrix is singular. So you have to find out determinant, you have to equate it to 0, then you are going to get that constant. Okay? So write that and do that fast. It should not take more than 1 minute. K is equal to 4. Yes, done? K is equal to 4. Okay, write the next. Find the value of k. Find the value of k such that rank of, write the matrix. It's a rectangular matrix now. It's a rectangular. 1, 1, minus 1, 1, 1 minus 1, k minus 1, 3, 1, 0, 1. 1, 1, minus 1, 1, 1 minus 1, k minus 1, 3, 1, 0, 1 is 2. Again here also the rank is 2. So you have to find out the value of k. See that it's not a square matrix, it's a rectangular matrix. Okay? And here you have said that rank of the matrix is 2. Again less than its order. Right? 3 by 4. How many rows are there? 3. And how many columns? 4. So what can be the rank for this? At most rank can be 3. Right? If you remember, yes, listen once. Rank. We have learned some properties on ranks. Rank of a matrix, okay, rank of a matrix is 0 when Rank of a matrix is 0, 1 when all the elements are zeros. When all the elements are zeros, right? So for a null matrix, rank is 0. Otherwise, means if it's a non-zero matrix, then its rank will be in between 1 and n. If it is a matrix of order n, then its rank will lie between 1 and n. And if it is a rectangular matrix of order m by n, suppose A is a matrix of order m by n, then rank of A will be less than or equal to minimum of m by n. Just like what we have written now. It's a 3 by 4 matrix, so its utmost rank can be 3, or its rank can be at most 3, maximum 3, right? So 3, 4, so you have to take minimum value, that is 3 there, but it will be less than or equal to 3. So what I wrote here, if A is a matrix of order m by n, then the rank will be less than or equal to minimum of m by n. Then what is the rank of an identity matrix? Identity matrix of order 3, you should ask me what is the order. Okay, according to the order, we will have the rank of identity matrix. Okay, row of in is equal to n. Rank of an identity matrix, why its order is equal to n? Why? Because identity matrix is a non-singular matrix. It's a non-singular matrix. Okay, and we have learned that if it is non-singular, then its rank will be equal to its order. Right? That's the reason rank of an identity matrix is same as its order. Okay? You did not tell me what is the value of k here. K value is 2. What did you do here? See that it's a rectangular, it's not a square matrix. Then 3 by 3 matrix which involves k. Consider any 3 by 3 matrix which involves k. Suppose you are considering this part which involves k, or consider first, third, fourth columns, or consider these 2 columns or these 3 columns. Okay, consider any 3 columns involving k, then you are going to get a square matrix. Find out determinant, equate it to 0 because its rank is less than its order, right? It should be a singular matrix. Equate the determinant to 0, then you are going to get the value of k. Okay? Did you get the value of k? What is that? 2. Then take the next one. Find the value of k. Find the value of k if rank of A is 2. If the rank of A is 2, where A is equal to 0, 1, minus 3, minus 1, 1, 0, 1, 1, 3, 1, 0, 2, 1, 1, k 0. Again its rank is also 2, but see that it is a 4 by 4 matrix. Then what you are going to do? It's a square matrix, but even then what is said is its rank is 2. So what we should do? We have to consider a 3 by 3 matrix, 3 by 3 matrix which is involving k, and find out its determinant, equate it to 0. Yes. Done? Now write some points. Yes. Write some points. Then after that I'll tell you echelon form. Okay, because based on these also we can expect some objectives. So write some points first. Write that every square matrix can be expressed as the sum of symmetric and skew symmetric matrices uniquely. the sum of symmetric and skew symmetric matrices uniquely. Okay, in only one way we can express it. Even if we are trying to express it in another way, it will be same as the previous one. Okay. Similarly, right there, every square matrix can be expressed as the sum of Hermitian and skew Hermitian matrices. Hermitian and skew Hermitian matrices uniquely. Hermitian and skew Hermitian matrices uniquely. Okay? You take any square matrix, you can write it as the sum of symmetric and skew symmetric matrices. How? You have learned that. First part, okay, we'll write it as half of A plus A transpose. Right beside that statement, what we wrote the first statement, beside that right there, A is equal to P plus Q. Beside that first statement, A is equal to P plus Q, where P is symmetric and Q is skew symmetric. This P is written as half of A plus A transpose, and this Q is written as half of A minus A transpose. Any matrix can be expressed in this way, but see that when you solve it, you are going to get back again the same one. Half of A plus A transpose plus half of A minus A transpose, you are going to get A again. So you are just expressing them in this way, such that the first part becomes symmetric and the second part becomes skew symmetric. Okay? Similarly, you can write for Hermitian and skew Hermitian also. Okay? For the second statement, you can write there also A is equal to P plus Q, where P is Hermitian and Q is skew Hermitian. Here in this case, P will be in terms of Hermitian and skew Hermitian. So A conjugate transpose equal to A conjugate transpose equal to minus A. So it should be in that way. So this becomes half of A plus A conjugate transpose, half of A minus A conjugate transpose. Half of A minus A conjugate transpose. It will be in that way. Because the problem may be given and you may be asked to split it. So you should know that symmetric part and skew symmetric part. Write the next. Done with that? Write the next point. Inverse of a non-singular matrix. Inverse of a non-singular matrix is inverse of a non-singular symmetric matrix is symmetric. Then write the second point below that. If A is symmetric, then adjoint of A is also symmetric. Because in the MCQs we have all these type of questions. So first I want to give these points, then we can do the MCQs. Then write the next. If A and B are orthogonal matrices, of order n, then AB is also an orthogonal matrix. If both are orthogonal and they are of same order, then AB is also an orthogonal matrix. The next. Inverse of an orthogonal matrix is orthogonal, and transpose of an orthogonal matrix is orthogonal. Inverse and transpose will result in the same original matrix. Inverse and transpose will give you the same orthogonal matrix. Okay, the next. See that we wrote every matrix can be written as symmetric plus skew symmetric. Then we wrote it as Hermitian and skew Hermitian. Then write the next point. Every Hermitian matrix can be written as A plus IB, capital A plus IB, where A is real symmetric and B is real skew symmetric. B is real skew symmetric. Skew symmetric. When it is a Hermitian matrix, we are able to write it in this way, where A and B are the real symmetric and real skew symmetric parts. Okay. The next, inverse of a unitary matrix is unitary, same as orthogonal, what we wrote just now. Inverse of a unitary matrix is unitary, and transpose of a unitary matrix is unitary, same as orthogonal, what we have learned. Okay. And the remaining all I gave here. Then we'll see the echelon form. Yes, I took some matrix 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so we'll see how to do that, or how to reduce it to echelon form. How to reduce it to echelon form. Then we'll do problems on that. Okay, I'll tell you one problem of normal also. If required, you can do that, but we are not going to waste time on that. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9. Yes, in different books it is given in different ways, but I usually tell in this way. If it is a square matrix, yes, square matrix, draw a diagonal like that. Draw a diagonal. If it is not a square matrix, suppose I take this as 1, 2, 3, 1, 4, 5, 6, 2, 7, 8, 9, 5, like this. Square, then I am able to draw the diagonal. For this also, consider only the square part. Consider only the square part. It doesn't mean that you should not evaluate this, or you should not use the operations on this. Okay, you have to, but when you consider, okay, to draw a diagonal, consider only the square part. So I'll take this part like this. So even if it is rectangular also, consider only the square part, draw the diagonal. But whenever you are applying the operations, apply it on all the elements. Okay. So in a short way, how to remember echelon form is, draw the diagonal, make the elements below the diagonal as 0. In a short way, draw the diagonal, make the elements below the diagonal as 0 by using row operations. By using row operations. Okay, not column operations. Making the elements above the diagonal as zeros by using column operations. But we are usually habituated to using row operations, so we'll do that only with row operations here. Okay. So what you have to do is, you have to make these elements as zeros. These elements as zeros. So in a shortcut way, that is, you have to remember, you have to draw the diagonal and you have to make all the elements below the principal diagonal as zeros, that's all. Okay. So first, by using this diagonal element, you have to make this element and this element as 0. Okay. The next, by using this diagonal element, you have to make this element as 0. Right. So 2 implies R2 minus 4R1, because I have to make this element as 0, which is 4. So I need to multiply this with 4 and I have to subtract it. Right. And here I have 7. So I need to multiply this with 7 and have to subtract it. Then I'll get these two answers as zeros. So row operations. And you have learned in matrices that by using or by applying elementary transformations, rank of a matrix will not change. Rank of a matrix will not change by applying the elementary transformations. So that's the reason we are applying elementary transformations. Its rank will not change. Okay. So here R2 implies R2 minus 4R1 and R3 implies R3 minus 7R1. Okay. So 1, 2, 3 as it is. then 4 minus 4 into 1, 0, 5 minus 4 into 2, 5 minus 8, so minus 3, then 6 minus 3 into 4, 6 minus 12, so minus 6, then 7 minus 7, 0, 8 minus 2 into 7, so 8 minus 14, so minus 6, then 9 minus 7 into 3, so 9 minus 21, so minus 9 minus 21. Okay, so first we make the first two column elements as zeros. It is applicable to any number of rows, any number of columns. Okay, then draw the diagonal again, then by using this element make this element as 0, using this make this as 0, or you can use one more operation there, divide this completely by minus 6. Okay, you can do in different ways, they are elementary transformations, you can apply in different ways, right? So R4, R3, here I am making this as 0 now, R3 implies R3 by 2 or you can write this as R3 minus 2 R2. In different ways we can write it, right? R3 by 2 minus R2, or I will write that as R3 minus 2 R2. Okay, then this gives 1, 2, 3, 0, minus 3, minus 6, then 0, minus 6, plus 6. So 0, minus 12, plus 12, 0. Then draw the diagonal again and check all the elements below the principal diagonal are zeros. Now it is reduced to echelon form. Yes. So what I said, you have to draw the diagonal, let it be a square matrix or a rectangular matrix. For a rectangular, how to do that I said. For a square matrix you will get the diagonal, okay, directly. After that you have to make the elements below the diagonal as zeros, okay, by using only row operations. First column elements we made as 0, then in the next trip second column elements we made it as 0. So you can see here all the elements below the diagonal are zeros now. Now it got reduced to echelon form. In echelon form you have to count number of non-zero rows. You have to count number of non-zero rows, then that will give you the rank of the matrix. 0 row, yes, a row with all zeros. With all zeros is called as 0 row. A row with at least one non-zero element will become a non-zero row. So this and these are non-zero rows. Okay, so we can say that rank of A is 2. Rank of A is 2. Okay, now write the problems fast, then I will tell you one problem on normal. Let's write this. 1 2 1 0, 1 2 1 0, minus 2 4 3 0, 1 0 2 minus 8, 1 2 1 0, minus 2 4 3 0, 1 0 2 minus 8. Even see the time, how much time it's taking. Okay, find the rank. See the time also I said. We have done one square matrix and I gave you another rectangular matrix 3. Write the next. Find the rank. 0, 1, 2, minus 2, 4, 0, 2, 6, 2, 1, 3, 1. 4 0 2 6 2 1 3 1. See that here the first diagonal element is 0. Diagonal element is 0. It started The first element is starting with 0, right? And you have learned that yes, whenever the diagonal element is 0, shuffle the rows and start doing. You have to shuffle them. If you are getting the diagonal element as 0, shuffle the rows and do that. Okay? If you are applying echelon, then the diagonal element should be non-zero. Otherwise you cannot do that. You have to start with the first row, right? Which one? Second square matrix you are saying. Even then. No. Start doing from the first part only, better. Don't change it. Because again you have to shuffle the columns. Yes, draw the diagonal right from the beginning, not from the middle. You won't get wrong, you won't get correct answers. Don't do that. Because it should become the triangular matrix. Again you have to shuffle the columns. Shuffling the columns is not allowed. Okay, shuffling the columns is not allowed when you are applying row operations. So don't do that, you will get wrong answers. As what is the rank? 2. So what I said is, if the diagonal element is 0, then you need to shuffle the rows. Shuffle the rows, then apply the procedure. Okay? You cannot shuffle the columns. Remember that. You cannot shuffle the columns when you are applying row operations. It is row echelon form. Answer these questions. Okay, some objectives are there. Then we'll see. Yes. Answer the questions. Okay, we'll take some change here. Then I'll tell you again the problems. Okay, some MCQs we'll see. Then we'll move on to the topic. Yes. Answer. To multiply a matrix. Listen. To multiply a matrix by a scalar k, multiply first bit any row by k, second bit every element by k, third bit any column by k. What we have to do? Every element by k, right? Okay, the next. Write this question, just a small matrix, and tell me the answer fast. If A equal to small matrix 3 minus 4 1 minus 1, 2 by 2 matrix 3 minus 4 1 minus 1, then A power n is okay. First answer for that, first option, 1 plus 2n minus 4n n 1 minus 2n. 1 plus 2n minus 4n n 1 minus 2n. First matrix. Second option B, 3 power n minus 4 whole power n 1 minus 1 whole power n. Shall I write? Okay. Okay, see I'll write the options. Yes. Tell me which option is right. You are given a small matrix and is asking to find A power n. Fast. Which option is right? First one? How many of you agree with first option? First option is right. So if you do that twice or thrice, you can generalize it. Finding that is a square a cube, okay, you can generalize it. Is that first option true? First option or second option? First one? Okay. Then second question. Third one. If capital A equal to 2 0 0 0 2 0 0 0 2 scalar matrix. Scalar matrix. A equal to 2 0 0 0 2 0 0 0 2 and B equal to, yes, it's a upper triangular matrix. B equal to 1 2 3 0 1 3 0 0 2. Then find determinant of AB. Determinant of AB. See how fastly you will tell the answer. 0. You should say very fastly. Why? It's a direct question. See that? What is determinant of AB? Property. Determinant of AB is? How you write determinant of AB? Determinant of A into determinant of B, right? So what is the determinant of A? You forgot that property, that yes. Try to recall. If it is a triangular matrix or if it is a diagonal matrix, then determinant is just product of diagonal elements. Determinant of triangular, determinant of diagonal is just product of diagonal elements. Product of diagonal elements. When it is a triangular matrix, it is a diagonal matrix. Now see that both are of that form. One is triangular and the other is diagonal. What is determinant of A now? Determinant of A. A. Determinant of B. So determinant of AB 16. Okay. So you can do in that way very fastly. The next. If A equal to, yes, again a small matrix, 3 2 1 4. A is equal to 3 2 1 4. Then A into adjoint of A equal to 3 2 1 4. 2 by 2 matrix. 3 2 1 4. Then A into adjoint of A into adjoint of A equal to, options are 10 0 0 10, first option, 10 0 0 10, first option. Second option 0 10 10 0, 0 10 10 0. Third option 10 1 1 10. Fourth option none. Fourth option none. Option 1. Yes. What is the correct option? Are you calculating A into adjoint of A? Yes. You know that adjoint of A is equal to A inverse is equal to adjoint of A by determinant A. So multiply both sides by A. Multiply both sides by A. What is the determinant of A here? What is the determinant of A? 10. Then put it in that form. Put it in that form. Then next, if A is a square matrix, listen, just tell me the answer. If A is a square matrix such that A into A transpose equal to I, then the value of A transpose into A is I. Okay. A square matrix A is orthogonal if and only if A is equal to A square, A transpose equal to A inverse, A inverse equal to I. Three options are there. A is equal to A square, A transpose equal to A inverse, A inverse is equal to I. A transpose equal to A inverse. Why? Because A into A transpose is I. So send that the other side, then you are going to get that. Okay. The next, inverse of, write the next question. Inverse of has 3 by 3 matrix. 1, 2, minus 2. 1, 2, minus 2. Minus 1, 3, 0. 0, minus 2, 1. Okay. Is, now write the other 3 by 3 matrix. 3, 2, 6. 1, 1, K. 2, 2, 5. Then what is the value of K? Then what is the value of K? You know A inverse is equal to adjoint by determinant, right? S. And how you calculate adjoint? Do you remember? Adjoint. Do you remember adjoint? How we calculate adjoint? By taking cofactors, then alternate plus minus gives the cofactors. Then what we have to do? Transpose of the cofactor matrix will give you adjoint, right? So anyone tell me what are the adjoint cofactors of the first row? First row 3, minus 1, 2. See that, are they right? Do you remember? Leaving first element, that is leaving first row and first column, you have to take the remaining matrix determinant and you have to multiply with minus sign, minus 1 whole to the power of I plus j, right? So are those values right? So similarly calculate the remaining part and take the transpose. What is second row? Second row, as 3 minus 1, 2, the second row elements, cofactors. Second row, 0, 2, is that right? 0, this is minus 6. 2, 1, 2. Is that correct? Is that 2, 1, 2 right? What about third row? 6, 2, 6, 2, 5.
6 to 1.
2, 1, 2 minus 6, 2, 1. Is that last row minus 6 to 1? 6 plus 6. 6 to 1. Okay. Then take the transpose. If you take the transpose, 3 to 6, minus 1, 1, 2, 2 to 1. Adjoint matrix is this. Then compare it with the given matrix and get the value of K. Which one? Is that 6 to 5 or 6 to 1? Let's check once again. Those cofactors are right. 3 minus 1, 2, 2, 1, 2 and 6 to 1, 6 to 5. Then what is the value of K? What is the value of K? K is 2. K is 2. Then we'll see solving system of equations. okay, by direct method and indirect methods. Do you remember finding ranks, rank of AB and rank of A? We'll write the augmented matrix AB, we'll club the matrix A with B, then we call it as an augmented matrix, right? We used to find the rank of AB, right? Rank of A and rank of AB, we'll equate them. Do you remember? Okay, some example I'll take, some example. Yes, with that example I'll explain solving system of equations, okay, whether it is consistent or not. If consistent, how many solutions it will have. Okay, we have learned that if rank of A is equal to rank of AB is equal to n, number of unknowns, here number of unknowns are 3, x, y, z, right? If I suppose get rank of A and rank of AB as 3, then I'll get only one solution. System is consistent and it will have a unique solution. If suppose I get rank of A equal to 2, rank of AB is also 2, which is less than number of unknowns, because unknowns are 3. If I am getting rank of A and rank of AB less than 3, then I can say that the system is consistent, but it will have many solutions, infinite number of solutions. If suppose I get rank of A something and rank of AB something, means different, rank of AB and rank of A are not same, then we can say that the system is inconsistent. Okay. So first we'll write this in the form AX is equal to B, taking out the coefficients 1, 2, 5, minus 2, 5, minus 3, 3, minus 6, 2, x, y, z, 10, 5, 8. AX is equal to B form. Then we'll write its augmented matrix first. Augmented matrix AB, which is equal to 1, 2, 5, 10, minus 2, 5, minus 3, 5, 3, minus 6, 2, 8. Then again the same procedure of reducing it to echelon form. Draw the diagonal and reduce it to echelon. Yes. Reduce it to echelon. Reduce it to echelon form fast. 1, 2, 5, 10, minus 2, 5, minus 3, 5, 3, minus 6, 2, 8. Till all the elements below the diagonal are zeros, you have to complete that, you have to continue that procedure. Yes, I took those numbers randomly. I took just like that. So you may get a bigger number also. Did you reduce it to echelon? What is the rank of AB? 3. Rank of AB is 3. What about rank of A? Rank of A is also 3. Okay. Rank of A is equal to rank of AB is equal to 3. If he says only to check whether it is consistent or inconsistent, then no need to take much pain in that, right? You may get some different numbers. Okay. If he says only consistent, inconsistent, just check rank of A is equal to rank of AB or not. Then you can write that it is consistent or not. Okay. If he says to find out the solution also, then you have to be little bit careful. Okay. And once you get the solution, you have to substitute in any of the equations and you have to check. In any of the 3 equations and you have to check. Suppose no method is mentioned, then what you will do? Suppose he gives 4 options, which one is the solution? What you will do? You have to substitute and you have to check the options, right? So if it is in the form of MCQs, then it's okay. You can do that directly also. But if it is asked to get the solution completely, then you have to do that in this way. Otherwise, you can put in any of the equations and you can check which one is the correct option, right? Let's write the next question. We will have a break of 10 minutes. Okay. So we'll do one more of non-homogeneous. Let's write this question. X minus 4y plus 7z equal to 14. X minus 4y plus 7z equal to 14, 1, 4. 3x plus 8y minus 2z equal to 13, 1, 3. 7x minus 8y plus 26z equal to 5. X minus 4y plus 7z equal to 14, 3x plus 8y minus 2z equal to 13, 7x minus 8y plus 26z equal to 5. Check whether it is consistent. If consistent, what type of solution you will get, you tell me. See that in all we need echelon form. So that's the reason I said that concentrate on that. Even in Gauss elimination method also we need echelon form only. Because it's also important, no? In written test, you will be given limited amount of time. 2. Rank of AB, 3. So it is inconsistent. Rank of A not equal to rank of AB. So therefore the given system is inconsistent. So options can be like this. Consistent, consistent with unique solution, consistent with infinite number of solutions, inconsistent. Like that the options will be given, so you have to check and you have to mark it, okay? Sometimes even they will give you the solution also according to, along with that, okay? Write the next. Find the value of P and Q. Find the value of P and Q so that the equations 2x plus 3y plus 5z equal to 9, 7x plus 3y plus 2z equal to 8, 7x plus 3y plus 2z equal to 8, 2x plus 3y plus pz, 2x plus 3y plus pz, pz equal to q, have first bit no solution, second bit unique solution, third infinite number of solutions. Infinite number of solutions. Again reduce it to echelon form and tell me what are the P and Q values. So question can be what are the values of P and Q for getting no solution. So some P values, Q values will be given, you have to mark whichever is right. So they can frame 3 questions from that. What can be the conditions for P and Q for getting unique solution? What can be the condition for getting no solution and so on? Yes, did you reduce it to echelon? Did you reduce it to echelon? Yes, tell me what is the last matrix you are getting, final matrix. Final matrix, anyone? Tell me the elements. 2, 3, 5, 9. 0 minus 1, 5. Minus 31. Minus 47. 0, 0. P minus 5. Q minus 9. Yes. This is the final matrix after reducing it to echelon. Now is asking for what values of P and Q. It will have no solution, infinite number of solutions and a unique solution. I already told you that if rank of A is equal to rank of AB, then it is consistent. If rank of A equal to rank of AB equal to number of variables or unknowns, then it will have unique solution. If rank of A equal to rank of AB but less than number of variables, it will have many solutions, infinite number of solutions. If rank of A is not matching with rank of AB, then no solution at all. It is called inconsistent system, right? Now look at this. Look at this. If I make P as 5, listen, P as 5 and Q as 9. If I take the values P as 5 and Q as 9, then what will be the rank of A? What will be the rank of A? What will be the rank of AB? 2. So therefore it will have infinitely many solutions. So we can write in that way. For P equal to 5 and Q equal to 9, rank of A equal to rank of AB, which is less than 3, so infinitely many solutions. Okay, once you get that, then it is clear that for which values it will have infinitely many, no solution and unique solution. Now look at this. If I make P as 5, but Q not equal to 9, then what happens? No solution. P is equal to 5, then A will have only 2 non-zero rows. If I make this as 0, then A contains only 2 non-zero rows. So rank of A is 2. But rank of AB will be 3 because this part is non-zero. Right? So right there. P equal to 5 and Q not equal to 9. P equal to 5 and Q not equal to 9. The system has no solution since rank of A is 2, rank of AB is 3. Okay? Now when it will have unique solution, tell me? When will it have a single solution? P is not equal to 5. Is that necessary? Only P not equal to 5 is sufficient. Q need not be equal to or not equal to 9. See that. If this is non-zero and if this is 0, listen, don't write P not equal to 5, Q not equal to 9. Q can be anything. This should be non-zero. This need not be non-zero because rank of A is equal to 3 and rank of AB is also 3 even though it is 0. Even though this is 0, okay, rank of AB will be 3. So what you have to write is P not equal to 5 and for any value of Q. P not equal to 5 and for any value of Q, okay, it has unique solution. Okay. So this was regarding non-homogeneous system of linear equations. Okay, we'll see homogeneous system where the right hand side will be completely 0. When the right hand side is 0, do we have the augmented matrix? No. So decision will be based on only rank of A. Only rank of A. If rank of A is equal to number of unknowns, rank of A is equal to number of unknowns, then how many solutions it will have? Unique. Same concept. Rank of A equal to rank of AB equal to n, then it had unique solution. And here also rank of A is equal to n, it will also have a unique solution. Okay, a single solution. And that single solution is called, it has some other name, trivial solution or zero solution. We don't call it as unique solution. Okay, a single solution will get, and that solution is a zero solution or trivial solution. Okay, when rank of A is less than number of unknowns, then here we told that it will have infinite number of solutions. Okay, here also we will have infinite number of solutions, but we don't call it as infinite number of solutions, we call it as non-trivial or non-zero solutions. Rank of A equal to n, only single solution, that is zero solution, trivial solution. If rank of A is less than n, then it will have many solutions, we call them as non-zero solution or non-trivial solutions. Okay. So write this, solve Just I will give one example. X minus 2y plus 3z is equal to 0 minus x plus 3y minus 5z is equal to 0, 5x minus 2y plus 2z is equal to 0. Some set I have given. Okay, a homogeneous system. X minus 2y plus 3z is equal to 0, minus x plus 3y minus 5z is equal to 0, 5x minus 2y plus 2z equal to 0. Then you will have only A, find out rank of A, then based on that you will have the decision. Reduce to echelon, what is the rank of A? 3. Then how many solutions it will have? Trivial solution, 0 solution or trivial solution. Okay. Write one note there. Write one note there. The homogeneous system of linear equations will have a non-trivial solution only if the matrix A is singular. Only if the matrix A is singular. Is that not right what we have written just now? Check. We wrote the same thing. Chudandi, if rank of A is less than n, then it will have infinitely many solutions, or we call them as non-zero solution or non-trivial. Now what we have written is same. So when will it have non-zero solutions? When the matrix A is singular or the determinant of A is 0. Okay, which is nothing but rank less than n. Right? So for a system to possess non-trivial solution, the matrix A should be singular. Okay, then only it will have non-zero solutions. Okay, we'll do one more. Let's write this. Solve. X plus 3y minus 2z equal to 0. X plus 3y minus 2z equal to 0. 2x minus y plus 4z equal to 0. X minus 11y plus 14z equal to 0. X minus 11y plus 14z equal to 0. Let's do that. Check whether it has non-zero solution or zero solution. It has non-zero. Non-zero. Okay, so what is the non-zero solution? How will you find out? Find out the non-zero solution and tell me. Because we need this process in eigenvalues and eigenvectors. From the homogeneous system, we need to find out the solution. So find out what will be the solution for that. 0, 0, 0 you can write, but here non-zero, so you have to find it out. Right? So what will be the non-zero solution in this? Yes? Can anyone tell me what is the last matrix? 1, 3, minus 2. Minus 7, 8. 0, 0, 0. Yes. Listen. You know, but you might have forgot. Okay, just see that once. After getting this, you have to write it again as Ax is equal to 0. In the beginning, you wrote that given matrix has Ax or given system has Ax is equal to 0. Right? So here again you need to rewrite it as Ax is equal to 0 after reducing it to echelon form. Okay? Here, rank of A equal to 2, which is less than number of unknowns. So non-zero solution will get here. Now how to find it out? Okay? So we'll see that Ax is equal to 0 will give you the solution again. So we can write this as 1, 3, minus 2, 0, minus 7, 8, 0, 0, 0, x, y, z equal to 0, 0, 0. Because we need this in eigenvalues and eigenvectors. That's the reason I am telling you that. Next topic we need this, eigenvalues and eigenvectors. Now we'll write this as 1 into x, 3 into y, minus 2 into z equal to 0. So we'll get that as x plus 3y minus 2z is equal to 0, 0x minus 7y plus 8z is equal to 0. Two equations with three unknowns. Okay? So three equations, three unknowns will have a single solution. But here two equations with three unknowns. So we have to choose one value. We have to choose one value, otherwise we won't get the solution. Okay? So let z is equal to some k. You have to check how many equations are less when compared to unknowns. Unknowns are 3, equations are 2, so 1 is less, so take one value. If suppose you have 3 unknowns but you have a single equation, how many are less? 2. So take 2 unknowns. You are free to choose 2 values there. What I said? 3 unknowns, 3 equations should be there to get the solution. But here 3 unknowns are there. I have only 2 equations, so I should take one element's value arbitrarily. So I am taking there z is equal to k. If suppose I have 3 unknowns and only one equation, then I am free to choose 2 values. Okay, only one equation if I have, then I am free to choose 2 values. So let z is equal to k, right? Then we will get this as minus 7y plus 8k is equal to 0. So y is equal to 8k by 7. Use this here, x plus 3k minus 2 into 8k by 7 is equal to 0. So x is equal to minus 3k what happened? Yes, I substitute in reverse. Correct. X is equal to 2k minus 24k by 7. Yes. X is equal to minus 10k by 7. Right? Now see that you are free to choose k value. K can be anything. So that's the reason we said that infinite number of solutions. K can be anything. You put k equal to 1, 2, 3, 4 and so on. So you will get infinitely many solutions. Okay, that's the reason we said there infinitely many solutions, right? So here capital X is equal to x, y, z values. So we'll write it as minus 10 by 7. Then y value is 8 by 7 and z value is 1 times of k. Okay, so like that we'll find out the solution where k can take any value. Okay, that we need in finding eigenvectors, because we'll have system of homogeneous equations only. Okay. Then we'll see one on Gauss elimination method, which is a direct method. Okay, the difference between direct method and indirect. Okay, in indirect method, okay, you can have a system of equations which may be consistent or inconsistent, which can have infinitely many solutions. Whereas when a direct method is given, okay, it should be given for a system which has solution. A system which has solution, which should be consistent. Direct method we cannot apply for all the methods, for all the type of problems. Whereas the indirect method, which is based on ranks, you can apply it to any system. You can apply it to any system. It may be homogeneous, it may be non-homogeneous, it can be consistent, inconsistent, it can have infinitely many solutions also. Whereas whenever the direct method is given, it will be given only for a system which has solution, which has only a single solution. You cannot apply it when it is inconsistent or when it has infinitely many solutions. Okay? So in that you have learned about Cramer's rule, matrix inversion, Gauss-Jordan in your intermediate, right? Here you have learned about Gauss elimination. Gauss elimination method is a very simple method which is again based on reducing it to echelon. Again based on reducing it to echelon. You have to reduce it to echelon, then by using backward substitution method you have to get the solution. It's very easy when compared to matrix inversion and all. You have to just reduce it to echelon, by back substitution process you have to get the values. Okay, shall we see one problem, Gauss elimination? So shall we take the same? Take the same, just I made right hand side as 1, 2, 3. Same question, I made the right hand side as 1, 2, 3. Yes, here reducing it to echelon, but no need to find out rank. Why? See that we use that rank concept to check whether the system is consistent or not, but here not at all required. When a direct method is given, it will be given for the system which is consistent already. Direct method we can apply only when it is consistent. So you need not check the rank of A and rank of AB. Just you need to reduce it to echelon form. That's all. Then by using backward substitution procedure, you have to get the values of x, y, z. No need of finding ranks. Just you have to reduce it to echelon. Okay. So I'll write AB, augmented matrix AB. So which is 1, minus 2, 3, 1, minus 1, 3, minus 5, 2, 5, minus 2, 2, 3. Reduce it to echelon. If you want, you can shuffle the rows. If you want, you can shuffle the rows. I told you that sometimes diagonal element contains zeros. So you can shuffle the rows, but you cannot shuffle the columns. If you shuffle the columns, you will get wrong answers. Don't do that. Don't shuffle the columns. Shuffle the rows. If you want, you can shuffle the rows. When you are applying row echelon, don't shuffle the columns. When you are applying column echelon, don't shuffle the rows. As did you reduce it to echelon? Reduce it to echelon? Yes. The final matrix may be different according to the row operations or whatever you have used there. Okay, it may be different from person to person, but the final answer should be same. So anyone tell me the last matrix, what you got? 1, minus 2, 3, 1, 3, minus 26. Yes. Look at this. Here we are not checking what is the rank. Okay, we are not checking what is the rank. This is AB reduced to echelon form. Then you saw just now that have we found x, y, z values when the homogeneous system of linear equations is given. Similarly, you have to proceed in this case and you have to rewrite this as Ax is equal to B. You have to write it as Ax is equal to B. So I'll write that directly now. Ax equal to B form you have to take. Okay, multiply this with x, y, z equal to this. X, y, z, this. Okay, so x minus 2y plus 3z equal to 1, 0x plus y minus 2z is equal to 3, 0x, 0y plus 3z is equal to minus 26. Backward substitution procedure will apply here. First we'll get the z value from the last equation, then y value from the second equation, x value from the first equation. Such procedure is called backward substitution procedure. Okay, so from this I'll get z is equal to minus 26 by 3. Z is equal to minus 26 by 3. Using this here, y minus 2z is equal to 3, y minus 2 times of minus 26 by 3 is equal to 3, y is equal to 52 by 3, 3 minus. minus minus plus, so that will come here, 3 minus 52 by 3, so 9 minus 52 by 3, minus 43 by 3. Then after getting the value of y, substitute all these here, so x minus 2 into minus 43 by 3 plus 3 into z is equal to 1. Then that will give you the value of x. The numbers are a little bit bigger because I am taking the numbers randomly there. I will get 0, 0, 3 minus 26 or minus 25? Minus 26. So in that way you will get the values of x, y, z in Gauss elimination procedure, minus 5 by 3. We will see next how to find out inverse of a matrix. Inverse of a matrix by elementary row or column operations. You know already how to find out inverse by cofactors adjoint, right? Some matrix I took here randomly. A is equal to 1, 2, 3, minus 2, 3, 1, 3, 1, 2. You have learned that a matrix A is said to be invertible if there exists some other matrix B such that AB is equal to BA is equal to I. Then B is called the inverse of A is called the inverse of B, right? So that concept we are going to use here. Okay? So we write here A is equal to identity matrix into A, or A is equal to A into identity matrix. Once by using row operations we can calculate, the other by using column operations also we can calculate, where we get the form as AB is equal to I, BA is equal to I. So B becomes the inverse of A becomes the inverse of B. Okay? So that is the technique. Yes. A is equal to I3A, then we can write it as 1, 2, 3, minus 2, 3, 1, 3, 1, 2, 1, 0, 0, 0, 1, 0, 0, 0, 1 into A as it is. Yes. Whatever the row operations you are using on left hand side, you have to use the same row operation on the right hand side also. So when this left hand side becomes identity matrix, this becomes an inverse matrix. Okay? Whatever the row operations you are applying here, you have to use the same row operations here. When this gets transformed to identity matrix, this gets transformed to inverse matrix. Okay? Here you have to use the Gauss-Jordan procedure. By using the first element, we have to make this and this as 0. By using this element, we have to make this and this as 0. By using this element, we have to make this and this as 0. This becomes identity, this becomes inverse. Okay? So try doing. Use the diagonal elements and make all the other elements as zeros. So last half an hour is there. So try to do in that way. Meanwhile, I'll ask some MCQs. Okay, try to give the answer. The matrix A equal to, write the 2 by 2 matrix, A plus IC, elements A plus IC, minus B plus ID, B plus ID, 2 by 2 matrix only, 2 by 2, B plus ID, A minus IC, okay, is unitary. Is unitary if and only if A square plus B square plus C square plus D square equal to, option A is 0, option B 1, option C minus 1, option D I. Unitary. What is the condition for unitary? A into A conjugate transpose, because we are dealing with complex matrices. A into A conjugate transpose equal to A conjugate transpose into A equal to I. Do that and tell me the answer fast. It's a 2 by 2, no? You can do fastly. First find out A conjugate. What is A conjugate? A plus IB will become A minus IB. I told you that conjugates you have to find out. What are the conjugates? A minus IC, yeah? Minus B minus ID. B minus ID. A plus IC. This is A conjugate. Then A conjugate transpose we need, right? A conjugate transpose. So transpose A minus IC minus B minus ID, B minus ID, A plus IC. Then A into A conjugate transpose equal to I, then we say that it is unitary. A into A conjugate transpose equal to I. A is unitary if this is the condition. Then multiply these two. A plus IC minus B plus ID, B plus ID, A minus IC into A minus IC, B minus ID minus B minus ID, A plus IC. Multiply and equate it to identity matrix. Multiply and equate it to identity matrix. A into A conjugate transpose equal to I. What is the condition? A square plus B square plus C square plus D square is 1. Yes, 1. Listen this and tell me the answer. Every Hermitian matrix can be written as A plus IB, where A is real and first option symmetric, second option skew symmetric, third orthogonal, fourth none. Just now we wrote that, right? The next, every Hermitian matrix can be written as A plus IB, where B is real and symmetric, skew symmetric, orthogonal, none. Skew symmetric, right? The next, diagonal elements of a skew symmetric matrix are all skew symmetric matrix. Write a note. Diagonal elements of a skew symmetric matrix are all zeros. What about skew Hermitian? Write the next note. Diagonal elements of a skew Hermitian matrix are either all zeros or purely imaginary, because we are dealing with conjugates there, complex numbers are there, so therefore skew Hermitian diagonal element should be all zeros or it should contain purely imaginary numbers, I, 2i, 3i. Okay? Skew symmetric, only zeros. Skew Hermitian, zeros or purely imaginary. The next, if A is Hermitian, IA, small I into A is skew Hermitian. If A is Hermitian, small I into A is skew Hermitian and vice versa. A is Hermitian, when you are multiplying it with I, small I, then it becomes skew Hermitian. When you have skew Hermitian, if you multiply each element with I, it becomes Hermitian. Okay, that's the reason I said vice versa. If A is Hermitian, IA will become skew Hermitian. If A is skew Hermitian, IA will become Hermitian. The next. Rank of a unit matrix of order 4. 4. The next. By applying the elementary transformations to a matrix, its rank option doesn't change, decrease, increase, none, doesn't change. If A is on, look at this question. If A is a non-zero column vector, if you want to write that, if A is a non-zero column vector n by 1, then the rank of the matrix A into A transpose is, then the rank of the matrix A into A transpose is, options are 0, 1, n minus 1, n. I did not use none, n minus 1, n. 0, 1, n minus 1, n. A into A transpose, n by 1 is given, right? Is that right? 1, n. So when you have such question, take a small matrix. Why you go to n by 1, 2 by 1, 1 by 2, then you will come to know what is the answer. Take a small matrix and check, then you will get that correct answer. Take 2 by 1 matrix, 2 rows and 1 column. So whenever you have such big questions, take small, that sample and try to do that, then that will give you the right answer. Now what is the answer? What is the rank? If you are taking 2 by 1, 1. So 3 by 1 will also be 1, 4 by 1 will also be 1. So take a small question and check. Okay? If the rank of a matrix is 2, then the rank of a matrix A transpose is, what is the rank of A transpose? If the rank of a matrix A is 2, then what is its transpose rank? Its determinant is 0. Determinant is 0, so rank will be less than its order. Okay? The next. If A is a non-zero column matrix, write this, and B is a non-zero row matrix, non-zero column matrix, B is non-zero row matrix, then the rank of AB is, then the rank of AB is 0, 1, 2, 3. Again take the simple question and multiply and check. 1? Is that 1 or 2? 1. Next, the transpose of an orthogonal matrix is, inverse of an orthogonal matrix is, inverse of a unitary matrix is, transpose of unitary matrix. Okay, write this. The symmetric part of the matrix, whatever we have done, okay, on that just I am giving simple questions. The symmetric part of the matrix 1, 1, 2, minus 1, 1, 1, 3, minus 1, 2, 1, 1, 2, minus 1, 1, 1, 3, minus 1, 2 is symmetric part. I said that a square matrix can be written as sum of symmetric and skew symmetric. A is equal to P plus Q, where P is equal to half of A plus A transpose, Q is equal to half of A minus A transpose. Then what is the symmetric part you will get from that? Write the symmetric matrix from that. That first part is symmetric and the second part is skew symmetric, right? So whenever you are asked skew symmetric, find out A minus A transpose by 2. Whenever you are asked symmetric, find out A plus A transpose by 2. What is the answer? 1, 0, 5 by 2, 0, 1, 0, 5 by 2, 0, 2. Okay. The matrix, write this, the matrix A, H, G, A, H, G, H, B, F, G, F, C is, options are symmetric, skew symmetric, orthogonal, unitary. Symmetric, it's clear, but see the other options also. It's clearly given that symmetric, but you have other options also. It might be satisfying those also, no? Unitary is not applicable. Unitary is not applicable because it is a real matrix, right? Or real symmetric matrix. So unitary will not be applicable. Then check the other. Is that skew symmetric? No. Is that orthogonal now? Check. Symmetric, it's clearly given. But see the other options also. Yes, what is the answer? Symmetric only? It is not satisfying any other property? No. Orthogonal also no? It's only symmetric. Okay, then write the next question. If A and B are matrices and if AB is defined, then the rank of AB is equal to first bit rank of A, rank of B, third bit less than or equal to minimum of rank of A comma rank of B, minimum of rank of A comma rank of B, fourth option less than or equal to maximum of rank of A comma rank of B. First option rank of A, second option rank of B, third option less than or equal to minimum of rank of A comma rank of B, fourth option less than or equal to maximum of rank of A comma rank of B. Third, yes. Just like how we are seeing that order 3 by 4, 4 by 3, minimum of, okay, here also minimum of the two ranks we have to see, minimum of rank of A and rank of B, whichever is less, then that will be taken as the rank of AB. The next, if A is a non-singular and if B is any matrix such that AB is defined, then the rank of AB equal to options rank of A, rank of B, 1, 3. Rank of A, rank of B, 1, 3. If you have any doubt, you can take small example problems and you can do that, you can say. Take small problems and you can check. It means that B may or may not be. Yes? If A is non-singular and B may or may not be, then in that case AB is defined, then rank of AB equal to rank of B. Why? Because A is non-singular, so its rank will be more. Its rank will be more when compared to rank of B. And we have seen just now that the rank of AB should be less than or equal to minimum of rank of A comma rank of B. So minimum is rank of B. So answer will be rank of B. Okay? Chalo, okay. So tomorrow I'll start. Actually I wanted to continue with this eigenvalues, eigenvectors, but because they need some concepts of probability, okay, so I'll start probability part. But I told you that if you are able to do starting part easily, just introduction to probability part, then I'll continue with Bayes theorem and all. Okay.